Welcome back to Multigrid Methods. We're in Chapter 8. We talked about a few multi-level matrices previously in the previous section. We're going to review a couple of those definitions. And now we're going to talk about lots and lots of properties of these things. And in particular, we're going to try to get to the point where we can write the error transfer matrix for the various multigrid methods using these multi-level operators. Let me just switch back one or two slides. So there's this new operator, which is something that we haven't encountered before that we want to introduce into definition now. And so this is the so-called T matrix. This is the non-square T matrix, TJL, and it's defined as pi JL, which is the non-square Ritz projection, coarse grid Ritz projection matrix, minus the error transfer matrix for smoothing raised to the m power, and this is smoothing on the level j, times that same non-square coarse grid Ritz projection matrix pi JL. Now, if we want to square this thing up, make it a matrix which is NL by NL, then what we do is we pre-multiply by the prolongation from level J up to level L. Okay, so this is a new matrix called the multi-level T matrix. The one that we're going to be mostly interested in is this one, this square version of that. Okay, so and like some of the notation that I've used previously, when I square something up, I introduce a tilde symbol. And the way we do that most often is, or at least for the two cases that I'm aware of, is we multiply by this prolongation matrix or a prolongation matrix. The same thing happened whenever we wanted to define this pi tilde matrix. We define that as PJL times pi JL. Okay, so that the product of these two non-square matrices becomes square matrix, which is of size NL by NL. Okay, so I'll try to remind you this definition as we go along, but just wanted to call that to your attention again for now. Like I said, this definition comes with an M, and that is M here is going to represent the number of smoothing iterations, whether pre or post smoothing. If they're different, then this difference will become important and will be introduced here. But if it's known what that M is going to be, then we'll just simply drop this M. If for example, if it's understood that M is equal to 1, or it's the same number of pre and post smoothing steps, so that M1 equals M2 equals M, then we'll just drop it. Okay, so just wanted to make you aware of that. Now let's talk about some properties of these multi-level matrices. This is going to help us figure out how we can rewrite our error transfer matrices as products of these new multi-level matrices. So one of the first properties that I want to introduce is that the pi JL matrix times PJL, which is this guy here is of course the coarse grid, or sorry, the prolongation matrix. The product of these two matrices turn out to be the identity of size j. So this is the identity in our nj by nj. An interesting little property there. And we can also prove that in this little lemma, that the pi JL tilde matrix, which is a square matrix, is actually a prolongation matrix. Now, we're in the context of finite element methods where we know that the Galerkin condition holds. And so this is kind of a standard property of the fact that the Galerkin condition holds, as we'll see. Okay, so this one's a bit more puzzling. Let's prove that guy first. All right, so the Galerkin condition always holds in the following sense. This is a typo here. That should be, well, I should say the symbol's wrong, but the ID is correct. So this should be AL. It just has the wrong symbol attached to it. Okay, so in any case, the the uh the Galerkin condition holds. AJ equals RJL AL PJL. In other words, the wrap condition holds. By definition, this pi JL matrix, which is a non-square matrix, is equal to AJ inverse RJL, that's the restriction matrix, times AL. Okay? This matrix is non-square, and so let's post-multiply it by the prolongation matrix. So do the product pi JL times PJL. All right, so this becomes AJ inverse RJL AL PJL. But notice that this is just AJ because of this condition here. Remember, this AJ satisfies the wrap condition. Satisfies the Galerkin condition. So this can just be replaced by AJ. AJ inverse times AJ is just the identity matrix of size J. So that proves the first part. What about the second part? Second part, we want to show that the pi tilde matrix is actually a prolongation matrix. Well, that becomes pretty simple with the the identity that we just proved. So by definition, pi JL tilde is equal to PJL pi JL. And of course, if I'm multiplying by itself again, then I just repeat that. But now I see that this matrix here is just the identity matrix of size J. That allows me to write this product as just that, which is of course just the pi tilde matrix. Okay, so this becomes identity, and so I can collapse this product. So basically this goes away, and I just have pi JL or PJL times pi JL, which is the pi tilde matrix. So that's an easy way to see that this matrix pi JL is a tilde is a projection matrix. Remember, that's the property of a projection matrix. Any matrix that has the property that b squared is equal to b is what we call a projection matrix. So that's a projection matrix. Cool. Let's go on to another property. Actually, let's do a definition first. Sorry. So again, the way you should think about this setup is that J is a relatively, well, it's a very coarse version of the mesh, and it's separated by quite a few levels from this fine level L. Now we're going to define TJ prime matrix. This guy is defined as pi JL minus KJ star M times pi JL. The only difference between this and TJL matrix is that I'm putting a star here on this matrix K. So this matrix here, remember, that is the error transfer matrix for smoothing. Okay, it's defined as, so remember, KJ is defined as IJ minus SJ AJ. That's by definition. Now we showed that if you take the adjoint of this matrix with respect to the AJ inner product, then the adjoint of this matrix is IJ minus SJ transpose AJ. We showed that. This is the adjoint with respect to this inner product. Okay. So this is just a new definition, and we're going to define this prime matrix by replacing, it's exactly the same as the T matrix as we defined earlier, except that we replace this error transfer matrix for smoothing by its adjoint, KJ star. And in similar fashion, and here, by the way, we're already dropping M. We're not introducing M, although we could. We could put an M there and an M here as well. We're going to go ahead and drop those from the beginning. So we're going to define the square version of this matrix in the same way we always do. So if we want to define a square matrix, we're going to apply, at least in the few examples that we have so far, we're going to apply the prolongation matrix. This is the multi-level prolongation. Remember, this goes all the way from J up to L. It skips a bunch of levels in getting there. So if I multiply this times that, I get a non-square matrix, and that non-square matrix is precisely the pi JL tilde prime matrix. So I apologize that these don't have good names in English, but at least the symbols make sense. Okay, so suppose that J is strictly less than L, then we have the following properties. If I take the adjoint of the pi j L tilde matrix, then I get the same matrix back. So in other words, this is a statement which says this is self-adjoint, right? And if I take the star or the adjoint of this TJL tilde matrix, it's no longer self-adjoint. I get this new matrix that we just introduced, the TJL prime tilde matrix. So this guy here. That's what we get when we take the adjoint of the TJL, or I guess here, the TJL matrix. All right, so let's prove that. Let's prove that this is self-adjoint. This is not self-adjoint, but I get this new matrix which I just defined. Okay, so I think this proof is a little bit long, so bear with me. Okay, so let's recall a definition or a property, namely that R. So if let's see here. So if I want to compute this adjoint in the AL inner product, okay, so this is a square matrix of size NL by NL. And if I want to compute the adjoint, I throw it over to the other side, but as it goes over, it picks up the star. Okay, so this is by definition what we mean by the adjoint. So what I want to show then is that if I do some manipulations and move this guy to the other side, then whatever I get over here has to be the adjoint. So let's try to do that. In fact, what we're going to show is that when we do that manipulation, we move it to the other side, what we're going to get is the same matrix appearing. And so that's why it's self-adjoint. So let UL and VL be arbitrary. And by definition of this guy, this inner product becomes this. So what did I do here? I introduced the definition of the pi JL tilde matrix. And I also converted this inner product to a standard Euclidean L inner product by moving or attaching this matrix AL to one side or the other. I have a choice of either putting it here or in front of that vector over here. And I decided to put it on the right-hand side. So that changes the AL inner product to an L inner product. So what's next? The next thing I want to do is take the transpose of this matrix, and transposes happen in the usual transpose happens with respect to the Euclidean inner products. So when I move this guy over, it picks up a transpose, but of course, that is just the definition of the restriction matrix. All right, now I can use the definition of this pi JL matrix. It's AJ inverse RJL AL. Okay, everything else is the same. Oh, by the way, notice that whenever I did this transposition, I ratchet the size of that inner product. It goes from the inner product over R and L to the inner product over R, the Euclidean inner product over R and J. Okay, so now I'm using the definition. This guy is a symmetric matrix. So as long as I'm in the J inner product, I can throw that guy over to the other side. So it appears here because of symmetry. Let's see. So I can also move this guy to the other side, but it picks up a transpose as it does. And I also have to ratchet the inner product as I do that. But when I move that over, that gives me PAJ. So the whole thing, if I move that over, gives me a prolongation matrix. And what's left, the product of that just gives me the pi j L tilde matrix. And again, sorry, there's no good naming convention for this. It's just the symbols are a lot easier to write than say. So all I'm doing is taking the transposition to move that guy over to the other side. It becomes a P, and this whole thing is therefore just the pi j L tilde matrix. Now, finally, I can pull this AL matrix back out of the inner product and change this Euclidean inner product to an AL inner product, an energy inner product. So what we've shown is that as we move this guy to the other side, it doesn't have any star associated with it at all. But if this moves over to the other side, it has to be equal to the star. So that just means that it's its own adjoint, or in other words, it's self-adjoint. Okay? Now, let's have a look at this matrix, the TJL tilde matrix. By definition, that's equal to pi JL tilde minus the prolongation times the error transfer matrix times the pi JL matrix. All right. So remember that that came from the definition of the TJL matrix, which was pi JL minus KLM pi JL. And then I multiply that times a prolongation matrix to get back to the square matrix. But that's where that came from. If I multiply this guy times the prolongation matrix, I just get the tilde matrix. And of course, if I multiply this times the prolongation matrix, I just stack that guy on there. It's not any kind of matrix that we defined before. So this is what I have to work with. And we want to do the same sort of technique as we did before. We'll start with this guy on the left-hand side and try to move it over to the right-hand side and see what we get. So by definition, this guy is just equal to this or minus this. That's because this has two parts, right? And I'm going to use linearity of this AL inner product to write it as one inner product minus the second inner product. Now we know right away, and this just becomes a pain in the butt because we just have to carry this computation all the way down. This guy moves over to the other side immediately. We know that this is self-adjoint in the AL inner product, so it just goes over because of the last computation without any modification. It's its own adjoint, it's self-adjoint. So you can sort of neglect what goes on here. It's all the same. It's just copied all the way down. So what is really interesting is what goes on here, but it's all fairly simple stuff. It's again, what we do is we start out with AL inner product. We switch to the L inner product by introducing an AL, and we're going to put it over on the right-hand side. Then, of course, we do what you would expect. Move this guy to the other side. That ratchets the inner product from an L inner product to a J inner product. This becomes PJL transpose, but PJL transpose is RJL. It's the restriction matrix. Okay, what's next? Now I'm going to multiply by AJ times its inverse. So this is not changing anything. This is just the identity matrix. So if I do that, no problem, right? Just multiplying by the identity, that doesn't change anything. Next, what I want to do is, let's see, this guy. So I'm going to use a little property here. So for this product right here. So this does not change from going from here to here. But now where does this come from? Okay, so this comes from a little property which says that I can interchange this let's see. Let me make sure I'm saying the right thing here. Oh no. Okay. So I see. This is simpler than what I was making it. This I'm just going to pull out as to change the Euclidean inner product to an energy inner product. Okay. I was thinking there was some sort of um, identity that I was using, but it's much simpler than that. We're just pulling this guy out and creating an energy inner product. Okay, good. So now that's going to allow me to move this guy over to the other side. Once I do that, it comes over with the adjoint symbol. And that's because this thing is not necessarily self-adjoint. It comes over as it moves over through the energy inner product and gains a star. So this is truly the adjoint of this guy. But we know what the adjoint of this is. This is the adjoint of a product of things, right? So this m is some positive integer. And so the adjoint of a product is just a product of adjoints. Very simple. Okay. Actually, it's got to be you have to reverse the order the same as you do with transpositions, but this is a power. Okay, so it's a bunch of matrices which are all the same, so it doesn't matter. So I can just replace this with that. Okay, see what I'm doing? Replacing this with this guy here. So in one case, it's the adjoint of the products, and now I'm writing the product of adjoints. Okay, and as long as I'm careful there, I can do that replacement. That's equivalent. Next, what am I going to do? Let's see, what did I do going from here to here? It looks like I didn't do anything, did I? So I think I've got an extra line here, which is basically nothing, right? Let's check. Doesn't look like there's any change whatsoever going from here to here. What I do, what I've done in the past is as I'm typing this up, or maybe one of my students was typing it up, just copy a line thinking you're going to change it and then forgetting to actually change it. So this actually is just a repeated line. It doesn't need to be there. Okay, so but what I can do is just by examination. Oh, I think I know what I was going to do. I was probably going to combine this into one statement and write this as UL TJL tilde star. That's probably what I had intended to do. Or my student. I forget who typed this up. Okay, so let's see here. No, that's not right either. That's not right either. Let's think about this. Just a second. I think there's a missing step. Right? Because if I really want to conclude that, I have to move everything over, right? So this has to be just a UL here. So I'm going to need to move this guy over to the other side in the AL. So is that possible? So let's think about this. There's the thing I want. So I need to have this appearing on the other side. How do I get there? So I already have, or actually, no, I want something. What I want to appear on the other side is the star version of that. So I want TJL tilde prime. And so this should be KJ star M. So that's what I want to show up on the other side. So how close am I to getting that? Well, the only thing I'm missing is I'm missing this guy. Right? So let me copy it and then try to try to fill in that last bit of detail. So I want that guy to appear on the other side. So in other words, what I want to conclude is that I have UL P JL tilde prime VL. And I have to have it resolving in AL. So how do I do that? Well, what I need to do is write out what is the definition of this guy. So I need a little bit more work. So let's create a page here. Let's see. How do I add a new page? No, don't do that. The menu changed on me and I don't see how to add a page anymore. Does anybody know how to do that? I don't see it. Okay, I'm going to skip it then. And I'm just going to say, because I don't have enough room to do it here, just going to say an exercise. So here's what I think you need to do. So you need to replace this guy with its definition. So what's the definition of that? That's AJ inverse RJ L AL. All right, so you replace that with that. Then I bring the AJ up and that kills off this guy. Then I take this guy, RJL, throw it to the other side. It gains a transpose and becomes P, which is what I need. And then finally, I'm going to be in an L inner product, and I'm going to pull this guy down and change it to an AL inner product. So there's a couple of steps. I'm completely baffled why I failed to exhibit those. Although I'll have to go back in the notes, and maybe it is possible that they were in the notes, but just failed to copy correctly into the slides. So that also could have happened. But in any case, I'll leave that as an exercise for you to finish out the last few steps here. Again, you're going to replace this with its definition. Then you pull this AJ up and cancel that guy. Then you take the restriction, which is left over, throw it to the other side. It becomes a transpose, it gains a transpose, so it becomes prolongation. And then you convert the inner product, which is an L now, the Euclidean L inner product to an AL inner product by pulling this guy out. So there's roughly three steps there to finish that out. Okay, I apologize about that. So we'll fix those. I'll fix those slides up and we'll put the corrected ones. Oh, gosh, I just stopped reading. You know what? Um, okay, now I know exactly what happened. I really apologize. So I saw this. I saw that symbol there, and I thought, oh, there's nothing left. I'm at the end of this proof, so I've got to finish this up. But I wasn't done yet. I was just not paying attention. Okay, so that is not necessary. So go to the other side. So if I go to the other side, then the next thing I start with is exactly what I said. You go and use the definition of the pi JL matrix. That's that. Then I can bring this guy up and cancel that. Then I have an RJL. I'm going to throw the RJL over to the other side, becomes prolongation. You ratchet the inner product. And then finally, you pull this guy out and it becomes an energy inner product. Finally, you collect terms. So just what I said, but if I would have just been patient, I would have seen it. And we get what we want. So this has to be the adjoint. So that means that the adjoint is equal to the T prime tilde matrix. Okay. I apologize for that. It was I was thrown by a couple of things, namely this misplaced QED symbol, and then the fact that this appeared twice. It threw me off. All right, but let's go back. So yeah, so this is what we wanted to prove, and this is what we did prove. Okay, so this is self-adjoint in the energy inner product. This is not self-adjoint, but its adjoint is very simply stated. It's just the GJ L prime. Now, by the way, this guy could be self-adjoint, namely whenever this is self-adjoint. And this is self-adjoint precisely whenever I do symmetric smoothing. So it is possible that this guy can be equal to its own star. So this can be self-adjoint whenever we have, S, what was it, J transpose is equal to Sj. In other words, my smoothing iterator matrix is symmetric. Then this guy really will be self-adjoint. So just a small remark there. Okay, so in general, this guy, it may be self-adjoint, but it's never, in general, going to be a projection matrix. We do know, however, that the pi j L tilde matrix is a projection. As long as the Glerkin condition holds, this guy is a projection matrix. But this new T matrix is not a projection. Okay. All right, another interesting property which is going to help us with expressing error matrices in a nice and efficient way. This is the error that we make in the coarse grid rich projection matrix, I minus the coarse grid rich projection. I minus the TJ tilde matrix, this is also kind of like an error. But when I multiply these two things together, amazingly, I just get this matrix back. So this is a little bit like saying I have the property that A times B is equal to A. Okay, so what is this property? It's a little bit like saying B is kind of an identity when I multiply it by A. Not quite, but it has this interesting and weird property. And likewise, if I pre-multiply by this matrix, IL minus TJL star, remember this is the adjoint of this matrix in the L, or the energy inner product AL. If I multiply this times this error matrix, then I get the same matrix back. So this is a little bit like saying, what if I do B star times A, I get A. That's a curious property, isn't it? So we want to prove those things. All right, so let's start off by looking at investigating the right-hand side of that number 4. So, or actually, I probably meant to say, yeah, sorry, left-hand side of 4. That's right. Let's look at the left-hand side. So we need to FOIL this guy out. But of course, you need to be careful when you do FOIL properties, or FOIL process with matrices, because order matters in general, right? We don't necessarily have commuting matrices. So if I'm correct, then the left-hand side of that thing we want to prove, 4, is just equal to I minus pi j L tilde minus TJ L tilde plus the product of those two matrices. Now, let's look at this by definition. What is this guy by definition? So that's going to be PJL times PJL, TJL times TJL. But remember, when we do multiplication like this, we always get the identity. So that's something that we proved, and that was equation 1 in this slide deck. PJL times PJL is always the size J identity. Okay, so Now, this collapses then, and we just get PJL times TJL, and so this is just TJL tilde. So that guy is just TJL tilde, and it cancels with that. So clearly, ML is equal to this, just these two matrices here, because these two cancel each other. So I'm only left with that. Now the left-hand, similarly, the left-hand side of 5 is ML prime. What we're defining as ML prime. That's going to be IL TJL star minus pi JL plus TJL star pi JL. Okay, so now we're going to use again a definition. Okay, this product here is just going to be PJL TJL prime. This is a typo here because of that should not be, the notation is wrong. Should not be italicized. Okay, but by our definitions, this guy here is just equal to all of this stuff. All right, but now we're going to multiply pi JL times PJL and a pi JL times PJL. That's just the identity in both cases. All right, so I get identity here, identity with that product. Okay, when I multiply through by this guy on the, but it's multiplied on the right-hand side. So I just get this. All right, and this part here is just going to be equal to the pi j, or sorry, TJL. Oh, I see why it was wrong. It's because I switched somewhere along the line. I was using this notation, subscript J, superscript L, and I switched to just a J comma L. All right, so we replace that back with this is just going to be TJL prime. But when I multiply it times that, it gives me the TJL tilde prime. And TJL tilde prime is just equal to the star matrix. So let's see. Right, so this guy should cancel with this one, right? And so all we're left with is that. So this is a typo here. Gosh, lots of typos. The star should not be there. That's because whenever we do this product here, we get this matrix. And that means that this matrix and this matrix cancel each other. And all that's left is this. Okay, so let's recap what we've proven. So if I post multiply by this matrix here, then I'm just left with this original matrix. This is the error in the coarse grid ridge projection. If I pre-multiply by its adjoint, so this matrix, then I'm left again. So I pre-multiply this times that, and what I'm left with is just this guy. In other words, I get right back the error in the coarse grid projection. So these properties don't look like they're that interesting, but they become very powerful when we try to express error transfer matrices. Okay. Now, another lemma follows very quickly from the previous theorem, and it says that, well, if I pre-multiply by this matrix on this guy, then I get that matrix back. But then when I post-multiply by that matrix, I get the matrix back again. So the matrix, which is the error in the coarse grid ridge projection, is invariant to this pre and post multiplication. Okay, so in other words, we get this identity. This is very easy though, because we already have formula for this one and we have a formula for that one. Okay, so right, so let's start with this guy here. This is equal to this product. Then I'm going to come back and say how and where I use these two properties here. Okay, so this is equal to that because of the, right. Okay, so this is, so we said that this matrix is a projection matrix. The coarse grid Ritz projection matrix is a projection matrix, and therefore I minus that matrix is also going to be a projection matrix. In fact, that's a general theorem. If I know that P squared is equal to P, then I know that I minus P squared is equal to I minus P. So that's the property that I'm using here. I don't think I needed to do the proof in this more complicated way, but this is the way I chose, and it should work out. Okay, so I'm going to use the fact that this is a projection. And then I use the fact that this is equal to this matrix, and then this matrix is equal to that product matrix. And then finally, I can multiply this again times itself and just get the original because it's using the fact that it's a projection, and I get the identity that I wanted to show. I think it's even easier than that, but that's okay. This is still correct. All right, so this is the identity that we just proved. These two matrices, when I make this matrix product, leave this guy, this energy invariant. Kind of an interesting fact. All right, and then another, again, just a bunch of properties that is going to allow us to write the error transfer matrix in a simplified way. So bear with me on these seemingly endless technical lemmas. Suppose that I is strictly less than J, which is strictly less than L. So in terms of a picture, I've got this L at the top, J is at some level in the middle, which is well separated from this really coarse level I at the very bottom. Okay. And all I'm assuming about I is that it's greater than or equal to 0, strictly less than J, and J is strictly less than L. So somewhere down here is the 0 level. Then, if I multiply the prolongation matrix, TJL times this matrix, IJ minus TIJ tilde. So this is square and this is square. And I'm multiplying by a non-square matrix. So the whole thing becomes non-square. Then what I get is IL minus TIL matrix. So this is a square matrix and this is a square matrix. But notice that they're at different levels here. Okay. And let's see if this all makes sense in terms of multiplication. So this guy here is a matrix which is of size nj by nj. And what about this matrix here? This is going to be nl by nj. So these are indeed compatible for multiplication, and what I get out in the end is something which is nl by nj. Now, what about this guy here? So this matrix here is nl by nl square, and this matrix is nl by nj, non-square. And if I take the product, it is compatible for multiplication. I get nl by nj. Okay, so it does make sense in terms of sizes. But notice, so this is the T matrix with respect to, so going from level J down to level I, but it's square and it has size nj by nj. This is the T matrix going from level L down to level I. Okay. So on one hand, we have the T matrix going from, let's see, was J down to I. So that's this guy here. Let's write this in blue. Tij tilde. And that's square. And what about this guy here? That's going from level L all the way down to level I. And that's what we call IL tilde. Okay. So this is a rather interesting formula that we want to prove. Okay. And of course, it's the same prolongation matrix in both cases. So this is the prolongation matrix that goes from J up to L. J up to L. Okay. So let's see if we can prove this. So we're going to start out with this on the the left-hand side and try to show that we get to the left-hand side. Okay, so if I multiply through by this matrix here, what do we get? Oh no, that's not exactly what I'm doing here. What are we doing here? So this is all the same. And what is that guy? Oh, right. This is just the identity, right? That's just going to be an identity matrix. So I've just introduced this through one, that's the identity. Okay, so apparently we're going to need that for some reason. So let's multiply this out. We've got to do, we've got to keep track. We have two multiplications, essentially, two distributive properties. We got to go through here, here, and then I got to go here and here, right? So we get these terms. I'm going to leave this guy out in the end. Just leave that alone for now. And I get all that. Okay, so this is just going to be the pi j L tilde matrix by definition. What about this guy here? So the product of these two matrices here is just going to be PIL. Okay, PIL. If I multiply these two matrices, this says I'm going to take the prolongation from I up to J and then finally J up to L. So that's the same as the prolongation going from I all the way up to L. So that's that. That was a definition of the multi-level prolongation matrices that we had at the very beginning. This is by definition of the T matrix, Tij matrix. That's all that. And then finally, pi JL matrix is here. And I've left this guy out in the end. All right. Now I can multiply through by this matrix. I get that. And minus minus gives a plus. I get that. All right. What is next? This stays the same. This, of course, can be written as the this guy here. Actually, I probably should have done that more simply. Ah, no. Okay. Now, what about this? What about this? What happens when I multiply this matrix times that matrix? So that is just going to be the pi. Let's see, it's this one here. I think I have a typo with this guy, right? That one should also be IL. Because when I take a matrix like that, so pi j, pi ij, and pi jl. So let's look at the definitions of those guys. So it's going to be I inverse R ij aj, right? And then multiply by this guy. What is that guy? That's going to be aj inverse R j up to L AL. Okay, so these two matrices see each other and they give the identity. This matrix times this matrix just gives us RIL. And so what we get is AI inverse RIL AL, and that is just equal to the pi IL matrix. So when I multiply these two times each other, I get pi I L. I should have gotten pi I L here as well. So that's the what threw me off. That's a typo. That should be pi I L. Okay, but in either case, this product here, all this stuff here, is just minus TIL matrix, TIL tilde, actually. That's by definition. Then finally, I'm going to distribute this guy across these parentheses here, multiplying on the right. And so what I get is pi JL, PJL, pi JL. That's by definition of that, times PJL, and then TIL, PJL. Okay. Now, I can finish this up because now I can bring this guy, let's see, this guy here is the identity, right? So that's identity. And what about what's left? Well, what's left is just IL TIL tilde times PJL. Okay. And the key here is this insight that this is the identity matrix. And that is that identity or that equation one. So if we click on that, equation one says precisely that. Okay, so we use that. Oh, stop it in this equation. All right, so that's exactly what we wanted to prove. So this identity now holds. Okay, so this strange identity that we're going to use in the representation of an error. Okay, so we just have to put that in our back pocket. And a corollary to this is that, again, if I is strictly less than j, strictly less than L, then PJL, IJ minus pi j pi ij tilde is equal to IL minus pi IL tilde PJL. So this one's a little bit easier than the other one that we just proved. The previous one involved these T matrices, and this here involves the pi matrices. And I need to actually, this should be a homework exercise here. I forgot to assign that as homework exercise, but that it's actually simpler than the proof of this guy. All right, so we have all we need now. And so what we're going to do next is use all of these properties to rewrite our error transfer matrices for our common multigrid methods in a convenient way so that we can do a lot of simpler analysis. So all of this tedious business is out of the way, and now it's we're going to use that in order to effectively rewrite the error transfer matrix for the V cycle and the W cycle, etc. Okay, so let's dive into this next section, multigrid error transfer matrices and multiplicative forms. So the idea here is to use all that we learned in this section here with all of these complicated lemmas and formula, etc., to say something good or something nice about the error transfer matrices that we commonly find in these multigrid methods. Okay, so this one is I'm not going to lie to you. This is going to be you know, a challenge, but we can get through this. We can make it. So the idea is, suppose that we're in the normal setting of finite elements, and the only reason why I'm assuming finite elements is so that we can use all of our usual niceties like the Galerkin condition. That's the main thing, really. And suppose we consider the V-cycle algorithm where it's symmetrized. So the symmetric generic V-cycle algorithm. So M1 is equal to M2, which is equal to the common value M. V-cycle means P equals 1. And then we have this expression for the error transfer matrix. And It's not necessarily, so previously the only expression we had for our error transfer matrix was in some sort of recursive form. Well, now using these T matrices, we can write this as a product of error matrices. So here it is. So the error transfer matrix for the V cycle is, the drum roll, it's going to be KL star M times I minus this T matrix. So this T matrix goes from level L minus 1 to level L, or however you want to look at it, goes from level L down to L minus 1. And then you continue on in exactly the same fashion. Then there's going to be, the next one is going to be IL minus TL minus 2 star tilde L, and etc. all the way until we get down to level 1. IL minus T1 star L tilde. What's sandwiched in the middle is going to be the error of coarse grid Ritz projection, where I'm looking at the coarse grid Ritz projection going all the way down to level 0. And by the way, found another error. That star should not be there. No star. That's because we know that that matrix is already self-adjoint, so we don't have to add that. Then you start stacking these guys going in reverse order. So then I have this error matrix, IL minus T1L tilde. Then, of course, the next one would be IL minus T2L tilde. And you go all the way up until you get to level L minus 1, IL minus TL minus 1, L tilde. And then finally, to cap it off, we have the error transfer matrix for smoothing at level L times M. Okay, so the way we look at this is as follows. So if we have a symmetric V cycle, it's comprised of a bunch of errors, or the error for the symmetric V cycle is a bunch of errors, and they multiply by each other. Okay, they multiply through. So the first error that I encounter is the error in my pre-smoothing step at the finest level. Then I have some error, which is a combination of a coarse grid projection and smoothing error, and they stack on each other. They go all the way back until I get to the error in the coarse grid Ritz projection going all the way down to level 0. And then finally, it's like I'm going back up the other side of the V cycle. So remember, V cycle is kind of, you imagine going down, 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 and then finally going up, up, up till I get back to the top. So this is like level L up here, and then this is level 0 down here. Okay, so you can see how these matrices appear. So this one is associated with this. Then this guy is associated here. Next one will be here. This guy is going to be associated with that one. And then finally, this error is associated with the coarsest level. Then we go back up. This one is associated with this. This guy is associated here. And finally, I have smoothing error associated with that level. Okay, so that's a nice way of picturing what this error is. And it's nice in the sense that I don't require any sort of recursive definition for my error. It's all a straightforward product of a bunch of matrices, which is nice. The trouble is we actually have to prove this thing. So that's the kind of the heartache. So let's do that. All right. So let's see, we've got 10 minutes. I hope that we can get through this proof. Let's give it a shot. So let's define the quantity MJL. That's going to be IL minus pi JL tilde matrix. Okay, so this part here is square everywhere. Okay, that's good. So this must be a square matrix, plus PJL, EJ, pi JL. All right, so you probably can see why I'm defining this, and that's because these matrices are going to be part of the error transfer matrix. They're important parts of that. All right, so I'm going to define that for any j, which is strictly less than L, that guy there. This error is the error in the in the V cycle, but at level J. Remember what I'm interested in. I'm interested in expressing the error of the V cycle at level L. Now, whenever J is equal to 0, I can just define this error. There's no further error at any lower levels because this error is equal to 0 at level J equals 0. And that's because when I go all the way down to level J equals 0, then there is no multigrid error because my iteration at level 0 is just doing an exact solve. So that's why there's no error there. So that's why we get this guy whenever J is equal to 0. Okay. E0 is equal to 0. Now, MJL. So let's write this guy out. MJL, this is equal to IL minus pi JL tilde. So just repeating these guys. PJL, KJLM, sorry, KJ star M. So now I'm going to just use what I know about this definition from what we proved back in chapter 5. So this error here is equal to all of this stuff. Okay. That's that recursive definition of the error that we proved back in chapter 5. Okay, then pi JL there. Okay. All right, so now in other words, this matrix here is important because this fits the form of the thing that we just defined, only it's at the next level lower. So what this guy represents is MJ minus 1J, okay, right here. So you can see that there's some sort of recursive nature that I'm going to encounter here. Okay, so we just proved that according to this definition. All right, now let's look at PJL KJ star M. So where does this product come in? That's right here. So let's have a look at that guy. That we're going to show with a bunch of manipulations, which I'm going to skip actually, gives just IL minus TJL tilde star. You can either write star or prime here. It doesn't matter. They're the same thing. Times PJL. So in other words, this matrix doesn't commute with this matrix. If I want to put this matrix on the other side, then what I get is the product of these two matrices here. Okay. So again, that's just some details that you can show. I'm going to leave that alone so that we can finish maybe on time. Okay, so let's put this in our pocket. This is 11. PJL KJ star M is IL TJL star tilde PJL. Put that in your pocket. And similarly, we can do the same thing, but to so this matrix here is going to appear on the other side. So we want both of these guys. So that one appears there and this guy appears there. We want to know what those guys look like when I multiply them times this matrix in the middle here. Okay, so that's cool. And I'm also going to skip this one. And we're just going to assume that it's true. Basic manipulations. It just involves using that estimate 1 over and over again. Remember, estimate 1 said that if I had pi JL times PJL, I just get the J order J identity. Okay, so that, again, these two matrices don't commute. So if I move this guy in front of there, not necessarily going to give you what you want. So this guy here is going to be, so if I reverse the order of this guy, or if I want this guy multiplied first, then I actually show that this guy is equal to that. So you can see if things truly commuted, then what I would get is KJM pi JL is equal to pi JL, and then I would get KJM over here. But see, I don't get that. I get something a little bit more complicated. And now look at the structure of 11 and 12. So whenever I change the order for this guy, I wanted to have this guy appear first, then what I get is IL minus TJL tilde. Similarly, whenever I wanted this guy to, over here, what I got was IL minus TJL star tilde. Okay, so notice that kind of symmetry emerging. So I'm going to put 10, 11, and 12 together. And what I get from putting those last two computations together is when I interchange the K matrix and the P matrix, I get this now. And whenever I interchange the K matrix and the pi JL matrix, I get this. All right. Now, if I invoke 6, so 6 said, remember, I can rewrite this product here, okay, by 6 by prepending this matrix and this matrix. Okay, so that's what 6 was. All right. That matrix is just equal to the prepended multiplication of that times that matrix again. And post-pending this matrix here, which has a similar structure. Okay, so that was precisely 6. That allows me to write this guy with this product and this product pulled out. So in other words, I can write 6, or I can write using 6, this line here, use it as just this. And then I take a look at this thing, or eventually I'm going to take a look at this thing inside. Okay, so first of all, I have that matrix and that matrix on the outsides now. And I have, is this another one? No, okay, good. I thought it might be another case of me just writing the same line twice, but it's not. And now I'm going to pre and post multiply by these two factors here. Okay, so those things which were outside get moved inside, and once they do, then I can multiply them through to get this. And now I get some cancellation. I get this cancels with that. And all I'm left with now is this and that. Okay. So what I've just shown is that this can be rewritten at MJL can be rewritten as this product pre and post times this guy in the middle. So that's what this thing is after doing my cancellation. What's left is going to be the MJ minus 1 L matrix. That's really cool. Now I can keep doing this. I can keep performing manipulations like this. So for example, this guy now, I can rewrite that in another in a similar way and get more matrices which stack on the outside. So therefore, at the end of the day, I can show this matrix here, which is the thing that I want, is by continuing to change these matrices in here in the usual way, the way that I just demonstrated up here, by continually pulling out these T matrices. Okay, I can go lower and lower. So the next one would be L minus 4L, and I would get another product of these I minus T matrices until I go all the way to the bottom. And when I get to the bottom, I'm eventually going to run into this matrix here, IL minus pi L tilde 0. Is that right? Or should that be, I think, that should be reversed. So the smaller number should always come first. Smaller number should always come first. Okay, but in any case, I can go all the way to the bottom. This is all the way down to level 0. Okay, and that's where you have to stop. There's no more manipulations that you can do once you get to that level. All right, so now recall that EL is equal to KLM times ML minus 1L, and we just showed that this guy is equal to this product matrix. So this proves the result that we wanted, okay? So I'm going to have to stop there. So we've made it through, and we showed that this, after skipping a few steps, that we can rewrite this error transfer matrix for the V cycle in this convenient form. Okay, this is not a recursive form anymore. It's kind of recursive, but it at least it's not recursively defined. It's just a product of a bunch of matrices. Now, I haven't emphasized it yet, but this shows actually that the V cycle, or that the multigrid V cycle, is a multiplicative general linear iterative scheme. It's just a bunch of general linear iterative processes multiplied times each other, because each one of these is the error for a general linear iterative scheme, okay, all the way down to here. So that shows that that this multigrid is just some sort of multiplicative general linear iterative system process. So we're going to pick up there next time, and I'll stop here, and I'll take any questions that you guys have.